Okay, this lecture strictly is for third year students, enzymology, and it is going to um for the people that are taking BCH 301. Now, let's go straight into what's this the content of this course. I mean, this section of the course, not the whole course. What I will be explaining shortly. Number one, I'm going to be looking at enzyme kinetics. Okay, I believe by now you should have known what an enzyme is. So we are going to be going into the enzyme kinetics. Now we are going to be looking at the simplified treatment of enzyme substrate catalyzed reactions. We are going to look at inhibition and inhibition kinetics. We are going to look at isoenzyme, zymogen, and zymogen activation. We are going to also look at what enzyme and enzymes, what they are. Now, what do we expect that by the end of this lecture, you should have gotten conversant with some terminologies like the active site, enzyme substrate complex, initial velocity, steady state, um, rapid equilibrium, maximum velocity, Km, Kcat, turnover number, enzyme efficiency, and so on and so forth. Okay, you will also learn how to write the simple Michaelis-Menten Michaelis-Menten equation or Michaelis-Menten mechanism for enzyme catalyzed reaction. We should know how to derive the Michaelis-Menten equation. You should also know, very importantly, how to sketch the graph of your VO, which is the initial velocity versus the substrate concentration for an enzyme catalyzed reaction, and how you illustrate where what the Vmax is for the maximum velocity or the Michaelis-Menten constant. We will also do some transformation, how we transform this equation to obtain the Lineweaver-Burk plot, which we describe as a double reciprocal plot, the A-Hawkey diagram of plot, and then the henceforth plot. We are going to be looking at all this in a moment. Now, you're going to really know what isoenzymes are and then what zymogens are. Okay, we are going to look at the activation mechanism of some of these enzymes. Then we are going to explain enzymes and enzymes. So let's dive into enzyme kinetics. Now, when we look at this, these are simply two words, enzyme and kinetics. It will be funny if you don't know what an enzyme is in your third year. Okay, by definition, enzymes are simply defined as organic catalysts. Okay, but enzymes are not, like the inorganic catalysts, because for inorganic catalysts, we define them as compounds that speed up chemical reactions without getting involved in the reaction. But for enzyme get involved in the reaction, though they speed up the rate of chemical reaction, but they are involved in the reaction, in contrary to inorganic catalysts that don't get involved in the reaction. So always know these things. Now, let's dive into what kinetics is. We say that the study of reaction rates and how they change in response to changes in experimental parameters is known as kinetics. Simply put, kinetics is the study of the rate of reaction. Whatever changes and it affects the rate of reaction is what we study when we are looking at kinetics. Now, the concept or the things that is worthy of noting in this lecture is what what actually is kinetics. Okay, like I said before, that kinetics is the study of reaction rate or rate of reaction, or you can say velocity. Whenever you're talking about rate, how fast can you get to Enugu? How fast can you get to Iko? We are looking at their velocities, the speed. Okay, the study is what we are looking at when we're considering this as enzymes, and then we that study is called kinetics. And now, the study of enzyme kinetics is useful in measuring what? What do we use it for? Number one, we can use it in the measurement of the concentration of an enzyme in a mixture. When you have a reaction, a mixture of enzyme and substrate, the kinetics that we get will help you to know the concentration of the enzyme in the whole mixture. And you do that by looking at its catalytic activity. Okay, you use it in measuring the purity of an enzyme by looking at the specific activity. You use it in determining the um, analytic efficiency or specificity of different substrates. Okay, you can look at an enzyme, maybe an enzyme that can catalyze two different kind of substrates. You will know which one is better. For instance, something like hexase, which you can use to break down different um, hexoses. Okay, so you will know for this particular enzyme which of the hexoses does it prefer and does it work better with. So with kinetics, we can make this comparison. So you compare different forms of the same enzyme in different tissues. For instance, the glucose 6 phosphate dehydrogenase that you can find in the liver, you can find it in the muscles, you can find it everywhere. But then with kinetics, we know that the one in the liver, how it performs, or it outperforms the one in the other um, organs. So with kinetics, we can look at this comparison. Now, with kinetics, we can also look at the effect of inhibitors, okay, which can give us information about the catalytic mechanism, the structure of the active site, and the potential therapeutic agent. Many of you don't know that most drugs you take are all enzyme inhibitors. Okay, we are looking at their kinetics. We help you know what extent does it inhibit that enzyme. Now, then you also have to know that in the kinetics will enable you also to know the dependency or velocity on substrate concentration. Okay, as it is described in many enzymes by the Michaelis-Menten equation. In fact, we can't talk about the kinetics of enzyme without talking about the Michaelis-Menten equation. Now, Michaelis-Menten equation helps you to determine some kinetic parameters. And these kinetic parameters, we have the Km, which we call the Michaelis-Menten constant. We have the Kcat, which we call the turnover number, which relates the maximum velocity with the total enzyme or total active site concentration. Now, when in enzymology, we always um, look at enzyme concentration with total enzyme active site concentration. So whenever I'm saying total enzyme active site concentration, I'm still referring to total enzyme concentration. Now, another kinetic parameters is the relationship, the ratio between Kcat and Km. They are ratios which will enable us to determine the kinetic efficiency of the enzyme. Now also, the kinetic parameters can be determined graphically. Naturally, when we study rate of reaction, you normally determine these parameters. You determine it by plotting a graph and reading out these parameters from your graph. So we determine it graphically by measuring the velocity of the enzyme reaction at different substrate concentration. We are going to see all this in a moment. So let's look at a simple model of enzyme. Now, simply, an enzyme, first of all, binds with substrate. An enzyme binds, first of all, with substrate. So in this, the E is our enzyme is binding with the substrate. Okay. When the enzyme binds with the substrate, it forms the enzyme substrate complex, which is broken down into enzyme and to product. Now, because we are keeping this thing simple enough, this is what it should be. But in the real sense, this ES should be converted to another complex called EP. Okay, it's going to be transported to EP. EP is also another complex. Now, this EP can now break down into this, but for simplicity, we are not going to be looking at the EP stuff. Okay, we are not going to be looking at that. So let's look at the thing, the one we have now. In this model, the substrate reversibly associates with the enzyme E. Okay, in a first in the first step, binds this. Okay, and some of the resulting complex is allowed to break down to yield products and the free enzyme back. So what we are saying is that when S, when the enzyme E binds with S, it will form ES complex, like I said. And if you allow this to break down to give you your enzyme back in the original conformation. Okay. Now, we like to know how to recognize an enzyme that behaves according to this model. One way is to look at the enzyme kinetic behavior. Okay. Now, at low substrate concentration, at low, okay, one way is to look at the enzyme kinetic behavior at low substrate concentration and how it affects the rate. So we so we want to know what rate law such enzyme would obey. You understand? When we have an enzyme reaction, we are trying to look at when the substrate is low, what happens to the rate of reaction? And whatever we see in this rate of reaction will show us how this enzyme behaves. Now, if a newly discovered enzyme obeys the rate laws, then we can assume that it acts according to the model I just explained. Now, let's derive the, the laws first. Let's derive it. Now, we don't just jump into derivation, but as we go on, we are going to be making some assumption. Okay. For this model, we say let VO be our initial velocity for the reaction, the initial velocity or the initial rate of reaction. Okay. The letter stands for the appearance of product in the solution. So when you look at the rate at which products are formed, we can now begin to say that is the initial velocity. Okay. Now, and we represent that with the the equation dp, the dp over dt, whose phenomenological rate of reaction is the first order, and this is given is the first order of reaction. And this gives you that the VO, which is the initial velocity, is equal to k cat multiplied by ES. Because if ES is not do not break down in the forward reaction, then that reaction will not hold. So so VO is equal to K cat multiplied by ES. Initial velocity is equal to K cat multiplied by ES. Okay, so you must remember this because this is just the rate of reaction. Now, containing an experimental measurable dependent variable VO, we can measure this in the experiment. We can measure the rate of reaction. That's our VO. We can always measure our VO as the reaction, because remember I told us that VO measures the rate at which product is formed. So you can always see your product, you can always measure what quantity is formed per time. Okay, and we said it is equal to K cat multiplied by ES. So it will also help us to also measure the kinetic parameter K cat. So we will also see that it enables us to measure our K cards, okay? And then the other variable, which is the ES, is unknown. And it is unknown because once the reaction starts, even though we can measure the speed, but we cannot measure the amount of enzyme that binds to the substrate. So we call that an unknown parameter. So we can always try to use calculation to find the the ES at that time. Now, before proceeding, one should state and remember some implicit assumption. Like I told us that in doing this, we have to be working with some assumption. So as long as the initial velocity is considered, the concentration of the product can be neglected. Okay, in this, we can neglect the concentration of the product. That is, if we compare the product to the substrate, remember the reaction just starts. So we will also, it will help us know that the concentration of P, that is the product, will be very, very little and sometimes negligible, and the concentration of the substrate is far, far, far outweighs that of the, the enzyme. In other words, the enzyme equally is quite small. So why the reaction is going on is that enzyme binds, forms ES gets to product, releases enzyme will come again and bind to substrate. So the reaction keep going. For instance, if you have a booker and in that booker you're supposed to feed 2,000 students, you don't necessarily have to get 2,000 plates to do that. So even in weddings, okay, so what they will be doing is at a point, once you finish with the plate, you will wash the plate and use it to dish for another person. Now, so we say that these assumptions, which hold in most kinetic experiments performed in test tube at low enzyme concentration, are convenient when considering the mass concentration equation for the reactants. So another assumption we need to do, even though we are still going to look at this assumption, is that we are going to look at the substrate concentration as not changing. Yes, we are going to look at it as not changing because actually the total substrate concentration should have been the free substrate, the substrate that binds to enzyme, and then the substrate that have been transformed to product. Okay, but now we just approximate it and say that the total substrate concentration, I will say explain later. While enzyme, because we know our total enzyme which we added to the reaction mixture, it will all and once the reaction starts, it will be difficult to know the quantity that is free and the quantity that is bound. So we can say that the total enzyme will be equal to that free enzyme, okay, plus the bound enzyme. And we say there is possible of a formation of an EP, okay, but we are not considering it, at least at this level, we're not consider it. So having that at the back of our mind, we are going to look at two assumptions which will enable us derive the Michaelis-Menten equation. And the first one we are going to look at, the first assumption we are going to look at is the rapid equilibrium assumption, or what we call the steady state kinetics. Rapid equilibrium assumption, or what we call pre-steady state. Pre-steady state, that is before steady state is achieved. We will still look at another assumption which we call the steady state assumption. So in actually looking at these assumptions, in a single substrate enzyme catalyzed reaction, we must note that most enzyme catalyzed reactions are very fast reaction, very fast, okay, very fast reaction. At the onset of this reaction, the enzyme binds to the substrate, which is S, to give us a complex ES. And at the pre-steady state, this ES breaks down to give you E and S without the formation of the product. Okay, we are maybe in your final year we begin to look at um, the mechanisms of enzyme reaction, where we talk about their collision, where we talk about their proximity, and all that and all that. For now, let's just stay within this 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 understanding. So therefore, there will be an established equation between ES and ES. An established equation between okay, S and ES. So the rate of formation of we have the kinetic constant as K1, and the rates for the breakdown of ES, we have it as the kinetic um, constant as K minus 1. You can call it anything, but just know what it stands for. Now, some of the rapid equilibrium assumption or pre-steady state kinetic assumption are as follows. Number one assumption we do under this rapid equilibrium assumption is that change in P per time is equal to 0. In other words, we are saying that products are not yet formed. Okay, products are not yet formed. So the reaction is still battling with your E plus S giving you ES. ES is not broken down to form the product, rather ES is broken down to form E and S. Okay. Now, another assumption is that the substrate concentration is far, far, far greater than the enzyme concentration. Okay. This like so it then the third one is that the total substrate concentration is equal to substrate concentration. Okay. In other words, the amount of substrate concentration does not vary with the reaction because the substrate concentration outweighs it. For instance, let me just ask you, if you have a bag of rice and rats came and ate the bag in the night, in the morning, what is the quantity of rice remaining? It will still be one bag because the quantity that the rat ate is highly negligible. Now, you still have the E total, which is the E total free enzyme plus the bound enzyme. And we tried to explain before. Now, so what happened? Now, with the kinetic constant of K1 and K minus 1 as rate constant for the forward and backward reaction, respectively. Um, respectively. So the rate of forward and backward reaction could be calculated since we know their rates constant. So now the rate of the forward reaction is equal to K1 multiplying free enzyme concentration multiplying substrate concentration. Remember, once it comes to substrate concentration, we are not talking about free substrate concentration and bound substrate concentration. So substrate concentration remains substrate concentration. Now, the rate of the backward reaction will be K minus 1 multiplied by the ES concentration. So at equilibrium, we say that the rate of forward reaction will be equal to the rate of backward reaction. And this will give us that K1 multiplied by free enzyme concentration multiplied by S is equal to K minus 1 multiplied by ES. So we can make ES the constant of the formula. Remember, in solution, we don't know the quantity, so we can calculate the quantities if we know the other parameters. Now, this will give us that ES is equal to K1 over K minus 1, all multiplying E and S. So I may decide and give you the parameters and give you the free enzyme concentration and then the substrate concentration, and I will tell me to calculate for ES. You can do that. It is just by small calculation. But while we are still deriving this, you can see that the equation, the equilibrium constant of, because we are talking about when they are at equilibrium. So we have what we call equilibrium constant. And equilibrium constant is the rate for the backward reaction divided by the rate for the forward reaction. Okay. So it is simply that KD is equal to K minus 1 over K1. So the equilibrium constant Kd is equal to K minus 1, which is the rate constant for the backward reaction, divided by K1, which is the rate constant for the forward reaction. So if you invert that, we see that we have 1 over Kd will be equal to K1 over K minus 1, which we have seen in our equation. So if ES, as we have seen, is equal to K1 over K minus 1, um, multiplied by E multiplied by S. So you can remove the K1, um, you can remove the K1 and then K1 over K minus 1 and replace it with 1 over Kt, as you have seen, as you have seen in this. So we can change our K1 and replace it with this. Okay. Now, when we do that, we can now multiply both sides by Kd, and you're left with Kd multiplied by Es to give you E multiplied by Es. Now, remember that E is the free enzyme. Okay. The enzyme concentration we are calling E is the free enzyme. So if we remember one of the assumptions we have made, the last assumption, where we say that the E total is equal to the free enzyme plus the bound enzyme, which is our ES, we can calculate what E is. So E will be equal to the total enzyme minus the bound enzyme. And then when that happens, we are going to replace our E, we are going to replace our E, this equation, we are going to replace E. Remember, this is the E we are talking about. Okay. We are going to replace this particular E with our ET minus ES. And when you do that, you're left with this equation. Okay. So you see that Kd multiplying by ES will be equal to, you put in bracket the ET minus ES all multiplied by S. And when you open that bracket, you're having that Kd multiplied by ES is equal to ET multiplied by S minus ES multiplied by S. So what you do is that you collect like terms, and in collecting the like terms, what you will do is that you will take the whole of this and you transfer it to this side of the equation. And when you do that, the negative side crossing equality sign becomes plus, so that you now have Kd, you now have Kd multiplying ES plus ES multiplying S, or we give you ET multiplying S. Okay. Now, you will equally see that ES is constant in the right side of the equation. So you factorize by bringing out ES and then multiplying the Kd plus S to give you our E total multiplied by S. Now, when that happens, you can now make ES the subject of the formula to give by dividing both sides by Kd plus S. And when you do that, you're going to have your ES is equal to ET multiplied by S all over Kd or plus S. Now, remember that when we were talking about the rate of reaction, we say that the rate of reaction, or the initial rate of reaction, we say that VO is equal, we say that VO is equal to K cat multiplied by ES. So we are going to replace this ES with the equation above. So when you do that, you're going to substitute ES in the equation above, and then you will have that VO is equal to K cat multiply, you put in bracket, E total multiplied by S all over Kd multiplied by x. And when you do that, you are left with k cat multiply et multiplying s all over kd plus s. Now, but as the reaction progresses, when all the enzymes are completely saturated, there will not be any free enzyme. Okay. So if that happens, all the enzymes will be in the ES form. And this can only happen when you have reached the maximum velocity. Okay. Now, so at the maximum velocity, the Vmax will be equal to k cat multiplied by E total, which is what you have here. So we are going to replace this, call it the Vmax, okay? And when you call it the Vmax, we now have VO to be equal with Vmax multiplied by X all over KD plus S. Now, under normal conditions, the Kd, which is the dissociation constant, is different from Km, which is the Michaelis-Menten's equation, where the Michaelis-Menten's constant. Therefore, we know that under normal constancy, that our Kd cannot be equal to Km. Okay? But under the rapid equilibrium assumption or the pre-steady kinetics, because products are not formed, we can assume that Kd is equal to Km. Therefore, if this holds, we can now say that our VO will be equal, we can now say that our will be equal, VO will be equal to Vmax multiplying substrate concentration all over our Km plus S. This equation here is referred to as the Michaelis-Menten's equation, which shows us the behavior of an enzyme at low substrate concentration. Now, that is, we've looked at one assumption. Let's look at how we can derive this equation again using the steady state assumption. The steady state assumption. Now, in the steady state assumption, we look at our model again, that our enzyme E plus our substrate S will bind together to form our ES. Remember, in rapid equilibrium, we say that products are not formed, so and so on. But this time around, we are looking at a situation where this ES is broken down to give me free enzyme and then products. Okay, so the enzyme binding with the substrate, the rate of the kinetic constant is K1. And then also observe that ES is broken down in two directions. Okay, it's broken down back to our E plus S, and it's also broken down with the kinetic constant K cat to give me E and then the product. Okay, so so some of the steady state assumptions are as follows. The assumptions of the steady state. You know, we have assumptions of the rapid equilibrium, which is all. Now, the first and the most important assumption that are made is that at steady state kinetics, that the rate at which ES changes per time is equal to zero. Do you understand? Is equal to zero. So the rate at which ES is breaking down will be equal to the rate at which is formed. So at that particular time, you begin to see that there is no change in the concentration of ES. So we say that number one assumption, which is the ES over the TO, that means that at steady state kinetics, the rate of change of ES per time is constant. Now, the next one is that, which is what we say, the next three is what we borrowed from the other assumptions we made. So that our S concentration is greater than substrate concentration is greater than enzyme concentration. And then we say that the substrate concentration is total substrate concentration is equal to substrate concentration, which is say the change is very negligible. So we don't assume that there is any change, while our E total will be equal to the free enzyme plus the bound enzyme. Take note of these four assumptions. Now, we want to express VO in terms of the measurable kinetics that we have talked about before. You know, these experimental determined independent variables such as our substrate concentration, total enzyme concentration. So we can see how to test for the mechanism by experimental kinetics. So we must replace the unknown ES in that equation, that very one, okay, with what we are measuring. Okay, now we said that during the initial stage of the reaction, as long as the reaction velocity remains constant, the rate, the reaction is in a steady state with ES formed and consumed at the same rate. I've mentioned that. So now the rate of formation of ES from the equation we have seen is equal to K1. The rate of formation of ES will be equal to K1 multiplying by the free enzyme concentration multiplying by the substrate concentration. While the rate of consumption of ES is broken down in two ways. When it is being broken down into E and S, okay, it will be K minus 1 multiplied by ES. When it is being broken down to form products, which is actually the rate of the reaction, is K cat multiplied by ES. So the rate of consumption will be when we add these rates together. The breaking down to form the substrate, and the breaking down to form the reactants, and then the breakdown to form the product. So in the steady state, remember we said that at steady state, the rate of formation of ES will be equal to the rate of consumption of ES, which means that the K1 multiplying by E, the K1 multiplied by E will be equal to multiplied by E multiplied by S. That's this will be equal to this. Okay. Now we can make ES the subject of the formula. When we do that, you have to factorize this equation before. If you factorize this equation, you can now bring out your ES and divide, and divide the rest on the left side of the equation. So when you do that, you're going to have that your ES is equal to this equation. Okay. Now, a little adjustment will give us that our ES concentration will be equal to K1 over K minus 1 plus K cat, all multiplying E and S. Now, to simplify the equation above, we have to introduce the parameter Kn, which is given the Michaelis-Menten's constant, which is our Km. And what is this constant? We say that it is the sum of the rate of reactions for the consumption of Es, which is our K minus 1 plus K cat, all divided by the sum of the rate constant for the formation of Es. That is your K1. So the K1 is this. And now when you look at this the equation, you will find out that 1 over you will find out that 1 over Km will be equal to this. Okay? And that is exactly what you have in this place. So, so we are going to use that to replace our K1. So I have said that 1 over Kn is equal to K1 all over K minus 1 plus K cat. So if our ES, as we have seen, is equal to 1 of equal to K1 over K minus 1 plus K cat multiplying E and S, then our ES can simply be put 1 over Km multiplying E and S. So we can multiply both sides by ES, and then we get exactly what we are, are looking for. We get the equation below. But you should remember that this fourth assumption, that total enzyme is equal to free enzyme plus our ES. Okay? Now, if you make the free enzyme the subject of the formula, I have to color the rest so that you know that what we're talking about is free enzyme. Okay? It will be that the free enzyme is equal to the total enzyme minus the bound enzyme. So we are going to use this to replace our, to substitute for our E. So when you do that, we're going to have Km multiplied by ES will give you ET multiplied by ES in brackets, all multiplied by the substrate concentration. And when you open the bracket, you know, you're having Km multiplied by ES is equal to ET multiplied by S minus ES multiplied S. Okay? So the next thing you do is you collect like terms. There is ES here, and there is also ES here. So you're going to carry this whole of this to this side of the equation. And when you do that, when you carry it to that side of the equation, you're going to have Km minus Es plus Es plus multiplied by S is equals to your Et multiplied by S. So our ES, you can now bring out ES and then make that ES the subject of the formula. When you make ES the subject of the formula, you will get that ES will be equal to this whole thing. It will be equal to Et multiplied by S all over Km plus S. That is our ES. So remember that we say that the rate of reaction VO, the rate of reaction, which is our VO, okay, sorry, VO is equal to K cat multiplied by ES. So we are going to replace this ES in this equation. We are going to replace this ES. So when we substitute ES in the above equation, you're going to have that our VO is equal to K cat multiplying everything in that equation, which is ET multiplied by S, all divided by Km plus S. Now, our VO will then be K cat multiplied by E total multiplied by S all over Km plus S. But remember what I said before, that when all the enzyme sites are completely saturated, all the enzyme will be in the ES form, thereby making the ET to be equal to um to equal to ES. The maximum velocity the maximum velocity occurs when the enzyme is completely saturated. That is when all enzyme molecules are tied up with S, or forming, or that ES is equal to the total enzyme. Thus, Vmax will be equal to Vmax will be equal to our enzyme Vmax, which is the maximum velocity, will be equal to k cat multiplied by et. So we are just going to replace this in the above equation. We are going to replace this with Vmax. Okay? And when we do that, we have that VO is equal to Vmax multiplied by S all over Km plus S. This is the Michaelis-Menten's equation. This is the Michaelis-Menten's equation. And like I said, that you cannot do anything in kinetics without knowing this equation. So, um, moving forward, we can say, looking at the above equation, we can say this equation expresses the initial rate of reaction in terms of the measurable quantities. The initial concentration, initial substrate concentration S, two kinetic parameters Vmax and Km will be different for every enzyme substrate pairs. Every enzyme substrate test they will be different. Now, the equation is known as the Michaelis-Menten equation, like I said, and it describes the kinetic behavior of an enzyme that acts as that simple model. Now, when you actually look at the equation, you will find out that it looks exactly like a familiar um, mathematical equation. Y equals to A, where the Y is our VO, our A is our Vmax, YX is the substrate concentration, and then B is the K cat. I say that S is the substrate concentration. So now this equation is actually an equation for a rectangular hyperbola. So when you make a plot of this equation, you're going to have um, a plot that looks like this, okay? Having your maximum velocity where you have the rate. When we talk about rate, this rate actually is our VO. That is our rate. While this is a concentration of S, the substrate concentration. Don't mind me, but we just have to improvise. Now, wait, this is the substrate concentration. So now, further analysis revealed the physical meaning of Kn and the substrate concentration at which Vmax is half. Naturally, when we are defining our Kn, we define it as the substrate concentration at half the maximum velocity. We still talk about this. Okay, so in this, substituting Kn for S will give us that VO will be equal to half Vmax when you substitute that in our equation. Anywhere you see um, Kn, you put S, okay? You will just come down in that equation that VO is equal to S. And we want to try that. When you take the Michaelis-Menten's equation, replace your Vmax with your Kn with S and see what the equation will give. Okay. Now, thus, at a low now, thus, the low value for Kn indicates high affinity, indicates higher and stronger binding. Okay, then high values of Km will indicate lower affinity. Another meaningful limit to this function is found at vanishing small values of S when the value of S is tending towards zero. Okay, if S is tending towards zero, we find out that VO will be tending towards V over Km, all multiplying S. We are going to see this in a moment. Further analysis revealed the physical. Okay, we've talked about this. Sorry. Now, The kinetic parameter Vmax over Km, or rather its constant part, which is Kcat over Kn, often referred to as catalytic ability of the enzyme, is a direct measure of the efficiency of the enzyme in transforming the substrate. So Kcat over Kn combines two traditionally separated aspects of the enzyme catalysis: the effectiveness of transformation of bound products, that is the catalysis per second, which is the Kcat, is the and also the effectiveness of products of productive substrate binding, that is affinity. So 1 over Kcat, we have seen that 1 over Kn will always be a combination of all the kinetic constants, where you have K1 over K minus 1 plus Kcat. Now, so the equation VO minus Vmax multiplied by S all over Km plus S means that for an enzyme acting according to this simple model, okay, an enzyme is acting this. So a plot of VO against S, if we make a plot, we carried out experiments, we generated our rate of reactions, and we plot it against the substrate concentration. It will give us a rectangular hyperbole. It will give us a rectangular hyperbole. When the enzyme exhibits this kinetic behavior, unless we find other evidence to the contrary, we assume that they act according to this model that we have above. We will assume that the enzyme is acting according to this model that we have above. And we call them the Michaelis-Menten's enzymes. So this plot is what we call the rectangular hyperbole. Now, this also shows that the enzyme obeys two order of kinetic reaction. The first order reaction, in which the rate of reaction increases as the substrate concentration increases. Rate of reaction increases as substrate. So you can see as the rate of reaction is increasing, okay, substrate concentration is increasing. So when you increase the substrate concentration, you notice that this rate will keep on increasing until you notice that it gets to a place that substrate concentration, as this substrate concentration is increasing, as this substrate concentration is increasing, we are not seeing the corresponding increase in rate of reaction. Rather, the rate of reaction tends to remain constant. Okay. So in this first place, it is obeying the first order of reaction, but at this point, it's not obeying first order. In fact, it is obeying the second order, which is the zero order. Okay, where increase in substrate concentration does not produce an increase in rate of reaction, and this can only happen when there is saturation. So we say that this can happen when the enzyme is completely saturated. Now, also note when you're carrying out this reaction, you will agree with me that when you make a plot and it is curved, it is always difficult for us to read values from curves. So it is better to transform this Michaelis-Menten's equation to actually a straight line equation. So there are three transformations that are made. The first one is known as the Line-Weaver-Burk plot, which we call double reciprocal plot, the Eadie-Hofstee diagram, and then the Hens-Wolff plot. So we are going to look at these three plots in a moment. We are going to look at these three plots in a moment. It's not going to take us time. Just follow me. And whenever you don't understand anything, just rewind the video and then try to understand it. Now, the what happens is that we'll first of all take the inverse of both sides of this equation. When you take the inverse of both sides of the equation, you will you will see that 1 over v will give you, instead of having v max multiplied by s over km plus s, you are having kf plus s, km plus s all over v max plus s. So we are going to separate this fraction. When we separate them, we have the 1 over vo is equal to km plus v max multiplied by s plus our s over v max multiplied by x. So this s we cancel this x, and we are left with 1 over v max is equal to 1 over vo is equal to km over v max multiplied by 1 over s plus 1 over v max. Now, when you look at this final equation, it's showing you a straight line plot. And the straight line plot which shows you that y is equal to m multiplied by s plus c, where m is the slope of the graph, and then c is the constant at the y axis. So now we say that 1 over v o is our y, m is km over v max, and then s is our 1 over s is our x, and then our c will be equal to 1 over v max. So if you make the plot, you will see a plot that looks like this. Okay? And when you see this plot, you will agree with me that in this plot, whatever value we see here will be the value of our 1, because it is the intercept of that plot. It will be the value for 1 over v max. Okay? The slope of the graph is your km over v max, while the intercept on the 1 over s axis will give us minus 1 over km. Are we following? Okay. Now, remember, we always say that km is substrate concentration. Now, let's look at the Eddie-Hofty diagram. We take our Michaelis-Menten equation, we invert both sides as usual, and then when we invert it and we get our 1 over v is equal to km plus s all over v max multiplied by s. This time around, we are multiplying both sides by v max, and when we do that, we are going to have that v max multiplied by v max over v will be equal to the Vmax multiplying both sides, okay? Vmax multiplying by everything on top. So when you do that, you're going to see that this Vmax will cancel this Vmax, and then we are left with Am multiplied by x plus x, all divided by x. Now, when you separate that equation and multiply both sides by v, you're going to have, because when you multiply this side, it cancel out. So we have v max equal to, separating the equation, you have v plus um, km over s plus v plus s multiplied by s. So this will simply give us v over km all over s plus our v. Now, if we make v the subject of the formula, you will come with this equation: v into minus km multiplying v over s plus v max. Now, the only thing you're going to see here is that if you're going to make a plot of our v against v over s, the slope of that graph will be minus km, and the intercept on the v axis will be your V max. So this equation representing a straight line graph will show you that our V being our Y will actually give you the M as our minus Km, although this plot is the only plot that is negative. Okay, then our S will be V over S, and then our constant will be the V max. Now, the graph will look something like this. So with this, you can find your kinetic parameters. Then finally, let's look at the Hens-Wolf plot. Hens-Wolf plot. And in the Hens-Wolf plot, we take our mental equation again and graph both sides. It will give you 1 over V equals Km plus S all over V max S. Multiply both sides by S. And when you multiply both sides by S, you're going to have S over V, and it's going to give us this particular parameter. It's going to give us this particular um, equation. Okay. Now we are going to separate this equation, and when we separate the equation, we are going to have this. We actually separated the equation and rearranged it. That is why you have it that S over V will be equal to 1 over V max multiplying S, and it will plus Km over V max. Now, of when you make a plot of S over V against S, you're going to have your intercept, which is this, to be your Km over V max. And then you're going to have your slope, which is your M, as 1 over V max. Okay, 1 over V max will be the slope, while the intercept on the S axis will give you your Km. Now, let's have a review and understanding of this Km. We say that it is the kinetic activator constant or the Michaelis-Menten constant. Number one is that Km is a constant. Number two is that Km, being a constant, is derived from the rate constant, as we saw when we were deriving that equation. Now, Km under the true Michaelis-Menten condition is an estimate of the dissociation constant for E from S. Now, small value of Km means tight binding, high Km means weak binding. Let's look at Vmax. We say it is theoretical maximal velocity. Why we say it's theoretical is that in the real sense, it is not a constant. Okay? It is not a constant in the real sense, but we treat it as a constant because when you plot your graph, you find out that at once the enzyme is saturated, Vmax does not increase significantly. Now, Vmax is a theoretical maximal rate of reaction, but it is never achieved in reality. Now, to reach Vmax, you would want to have all the enzyme molecules tightly bound the substrate. Now, again, we say that Vmax is asymptotically approached as the substrate is increasing. So, at this, now let's look at the dual nature of the Michaelis-Menten equation. We say it's a combination of the zero order and the first order kinetics, which I explained um, before now. So when substrate concentration is low, the equation rate follows the first order reaction. When S is high, it follows the zero order reaction. And the reason is that when it is high, all the enzyme active sites are saturated. Now, the Michaelis-Menten equation describes a rectangular hyperbolic dependency of V on X. We also talk about a measurable catalytic activity, which is our K cat. Now, the K cat is a turnover number, and it is the number of substrate molecules converted to product by enzyme per unit time. And then when E is saturated with substrate, if the microelectronegative model fits, then our K cat will be equal to the Vmax all over total enzyme. Now, the value of K cat ranges from less than 1 per second to millions per second. So it is not really, it has various ranges depending on the enzyme that we are working on. So now we have to look at the catalytic efficiency, and it has a ratio of the K cat um, to the Km. Now, an estimate of how perfect the enzyme is. So K cat over Km is an apparently second order rate constant, and we say it measures how the enzyme performed when substrate concentration is low. The upper limit for K cat over Km is the diffusion limit, the rate at which E and S diffuse together. So it shows us how perfect the enzyme is. So here we come to the end. You can send your questions to the Telegram group or the WhatsApp group, and from there we take it, and more explanations will come when we meet in class. Thank you very much.